In this video, we'll continue with our discussion on chemical bonding and how to use those basic rules for drawing Lewis structures for more complex compounds and ions. So I'm going to cover drawing Lewis structures for ozone, O3, and carbonate, CO3 2 minus. And we notice that carbonate actually has a charge, and those rules that I first laid out will help us figure that out. But the real emphasis of this particular video is to focus on resonance. And we saw with the last video that carbon dioxide could have two valid Lewis structures. This one on the left and this one on the right. We said that the preferred Lewis structure was the one on the left because it followed basic bonding patterns, oxygen having 2 bonds and 2 lone pairs. In classes, as you move further ahead, you can see that you can actually calculate formal charge to determine this, but for now, that should be sufficient. The one on the left is the preferred Lewis structure, but this case where we have 2 valid Lewis structures for satisfying octets is referred to as resonance or resonance structures. So we're going to see the same case with ozone and carbonate. So O3, you're supposed to count the total number of valence electrons. So 3 times 6, I have 18 valence electrons. The central atom has to be the one furthest from fluorine. In this case, they're all the same, so I'll just do O, O, O. Now I got to connect the outer atoms to the central atom using bonds. 1 bond, 2 bonds, subtracting the number of electrons used in those bonds to connect them. 2 bonds, each bond has 2 electrons. I subtract 4 electrons. I have 14 electrons left over. How do I distribute the remaining electrons? First, I want to satisfy outer atoms octets using lone pairs. So these 2 outer atoms of oxygen I can satisfy by adding 6 more electrons because they have 2 in the bonds, and 6 electrons are basically 3 lone pairs. 2, 4, 6, 8, 10, 12. I used up 12, so I still have 2 valence electrons. So what do I do with those? If electrons remain, where am I putting them? On the central atom. Okay. There are the 2 electrons. I used them up. Go to the next step. If no electrons remain and the central atom has an octet, you're done. Okay. So if I look at the central atom oxygen, it does not have an octet. It only has 6 electrons around it, 2 bonds and a lone pair. So what do I need to do? I need to go to that last step I've been using. If no electrons remain and central atom does not have an octet, move lone pairs on terminal atoms to form multiple bonds. So what I could do is I could say, oh, I'm going to move this right there. And when I do that, I see that the central atom oxygen has an octet because it has a double bond, which 4 electrons, single bond, 6 electrons, and 1 lone pair. It has an octet. Now, I know some of you are thinking, well, wait a second. You took it for the oxygen on the left. Could I have done it from the right? Well, could I do it from this one? You're absolutely correct. Right? I could have. And really, there is no difference. These 2 structures are not only valid Lewis structured, they are equivalent Lewis structures. So this is resonance. These are two resonance structures. And the reason why this occurs is I'm drawing three-dimensional molecules on 2D flat, okay? So these are equivalent resonance structures. They're two different structures or drawn two different ways to satisfy an octet, but the reason why they're equivalent, they're actually the same thing. I could easily take either of these structures and do a 180-degree turn, and I'd have the same thing. So that's why these are referred to as equivalent resonance structures. In actuality, what we'll see in the future is that resonance shows us a hybrid of structures. So I just drew both of these, right? A double bond on the left or a double bond on the right. I called them equivalent Lewis structures or equivalent resonance structures. So in reality, there is no single bond and no double bond. There is a hybrid of single and double. And what you do is you notice with the oxygen bonds in ozone, they're a little bit shorter than a single bond, but a little bit longer than a double bond. And they're a little bit stronger in strength, harder to break than a single, but a little bit easier than double for both of these oxygens to the central atom. So it's a hybrid. So how do we represent the hybrid? By drawing both equivalent resonance structures. So where else do we see that? Well, we see that with the carbonate. Now, what I like about carbonate is all the examples I've done so far did not have a charge. And the thing about carbonate is we know it's a polyatomic ion. So it's an ion, and you could find carbonate, for example, in, sodium carbonate. That's an ionic compound. But why Lewis structures are so useful is they show how the carbonate polyatomic ion is held together through covalent bonds. Because carbon and oxygen are both nonmetals, they form covalent bonds and they share electrons. So the -2 charge just tells me that there has to be an extra 2 electrons to satisfy octets to hold this species together. So just like before, we got to count total valence electrons. How do we do that? 4 from carbon, group 4A. Each oxygen gives me 6A. And that -2 means there's an extra 2 electrons. So 3 times 6 is 18, plus 2 is 20, plus 4, I have 24 valence electrons for this carbonate species. And I'm going to use Lewis structures to show how it's held together covalently. So who's the central atom? Carbon is furthest. I'm going to form single bonds to hold it together. So that was 3 bonds. I used up 6 valence electrons. I have 18 left. What am I going to do with the 18? I'm going to first add them as lone pairs to satisfy octets. So 3 times 6, where do I get the 6? 3 lone pairs to give an octet to each oxygen. 3 times 6 is I used up 18. No electrons remain. Go to the next step. If no electrons remain and the central atom has an octet, you're done. Carbon does not have an octet. So what do I have to do? Again, fourth rule. If no electrons remain, then the central atom, you need to basically get a lone pair from a terminal atom that you thought was a lone pair to actually a multiple bond. And there you go. So now carbon has an octet. It's happy. It's satisfied. A lot of teachers, they want you, it's conventional to draw the 2 negative on the outside to show that this is a charged particle, but this is the correct answer. Now, I'm going to ask you, can we actually have resonance structures? Could I have taken it from the lone pair on the oxygen on the right. Yeah, if I look at this drawing and I just rotate it 120 degrees, what would I get? Running out of room here, sorry. I'd get that structure, which is pretty much the same as the one on top. It's just through a rotation of 120. Could I get another structure by rotating another 120 degrees? Sure. So all of these are valid Lewis structures, and they're all equivalent resonance structures. So there you go, resonance. In this case, equivalent resonance for carbonate, 3 equivalent resonance structures. I hope that helps you understand resonance. I hope that helps you understand Lewis dot structures and how to use charges. Thanks for tuning in.